Thermal stresses. This is another topic under analysis of strain. Now, it is widely known that changes in temperature will cause dimensional changes in a body. An increase in temperature will result in an expansion, whereas a temperature decrease produces what we call contraction. Now, this deformation is isotropic, which means that the deformation is the same in every direction and proportional to the temperature change. It follows that the associated strain, which is called the thermal strain, is given by the equation epsilon is equal to alpha times the change in temperature, wherein the constant alpha is a material property known as the coefficient of thermal expansion. And also, the change in T or delta T is the temperature change. Now, the coefficient of the thermal expansion represents the normal strain caused by a 1 degree change in temperature. Laser. 1 degree change in temperature. Now, by convention, delta T is taken to be positive when the temperature increases and negative when the temperature decreases. Thus, in the equation above, a positive delta T produces a positive strain or elongation, and negative delta T produces a negative strain or basically contraction. Now, the units for our alpha or our coefficient of thermal expansion, it can either be in terms of per degree Celsius for SI units and can also be in per degree Fahrenheit for US customary system. Now, usually the typical values of alpha are in the range, let's say 23 times 10 to the negative 6 per degrees Celsius for aluminum and 12 times 10 to the negative 6 per degrees Celsius for steel. But nevertheless, in all of the problems provided, the coefficient of thermal expansion will be given. However, what is required from everyone is to analyze the temperature change and analyze how a material will deform subjected to that given temperature change. Now, if we are talking about the thermal strain, if the temperature change is uniform throughout the body, the thermal strain is also uniform. Consequently, the change in any dimensional L of the body is given by elongation due to thermal is equal to your strain times our L. Basically, this formula here was already introduced prior. And just substituting our formula for our strain, this one here, which is equal to this formula. So therefore, elongation is in terms of temperature change is equal to alpha times change in temperature times L. Or in some textbooks, they will use elongation due to thermal is equal to alpha L times change in T. Now, why interchange the position of L and our symbol for change in T? So that they can easily memorize the formula by reading this as alat. Now, if the thermal deformation is permitted to occur freely by using expansion joints or roller supports, no internal forces will be induced in the body. Basically, the material is free to deform, right? However, there will be strain, but there will be no stress. In cases where the deformation of a body is restricted, either totally or partially, internal forces will develop that oppose the thermal expansion or contraction. The stresses caused by these internal forces are known as thermal stresses. So, if we try to recall the definition of stress, in terms of the formula provided, it has to be that our stress is equal to the force, or basically it reads our stress is directly proportional to the force being applied over where it is being applied, or force over area. So in order for stress to manifest, there has to be force. Now when we say due to temperature change, where does change in temperature, the deformation of the material, relate to the formation of stress? So basically, in cases wherein the material is restricted, say for example, if let's say this is a rigid wall and we have a material here, let's say this is steel, and then another portion here, this is also a rigid wall. If we change the temperature, if let's say that if this material elongates because of temperature change, this will move forward, right? Then as it moves forward, uh, as it reaches this end here, internal forces will manifest because this rigid wall will stop the elongation, or will prevent the material from further elongating. So that preventing portion of the rigid wall, at that point, internal forces will manifest. And if there is internal forces involved already, stress will manifest. The forces that result from temperature changes cannot be determined by equilibrium analysis alone. That is, these forces are statically indeterminate. Consequently, the analysis of thermal stresses follows the same principle that were used in statically indeterminate problem, which is, or rather which are, equilibrium, compatibility, and then Hooke's law. The only difference here is that we must now include thermal expansion in the analysis of the deformation. So basically the same thing. But here, we will be analyzing, we will be, the analysis involves looking at how the material will deform once temperature is added, and where and when will internal forces manifest inside the material. So basically, that's the analysis part for thermal stresses. Now, there is a guiding procedure as to how to derive the compatibility equations. First, remove the constraints that prevent the thermal deformation to occur freely. This procedure is sometimes referred to as relaxing the supports. Show the thermal deformation on a sketch using an exaggerated scale. Now, if you can notice, most of the procedure suggests us to do a sketch. In studies of rigid bodies, we call this a free body diagram, because solving these kinds of problem is really complicated. Therefore, the use of diagrams, sketches will really help. Next, apply the forces that are necessary to restore the specified conditions of constraint. Then add the deformations caused by these forces to the sketch that was drawn in the previous step. Now draw the magnitudes of the deformation so that they are compatible with the geometric constraints. So basically the same thing, right? If the analysis we say that the elongation of this material as compared to this material is equal, then elongation A is equal to elongation B. And then we substitute that with our linear elongation, which is PL over AE, which is what we did with our previous topic. So basically the same thing. Now, by inspection of the sketch, write the relationships between the thermal deformations and the deformations due to the constraint forces. If the material is free to move, then therefore there is no internal force. However, if there is restrictions, then in our compatibility we will include the elongation for which relates the possible internal force that will manifest inside our material. So basically, it is a combination of these two formulas. Elongation is equal to alpha L times the change in T, and also elongation, which is equal to PL over AE, which is equal to stress L over A. So for thermal stresses, these two equations will is useful, because if you can notice, we're talking of the same elongation here. So if you are to substitute this portion to here, so this becomes stress L over E is equal to alpha L change in T. Now granting that the material has the same, is uniform in length, so therefore this cancels out. So stress is equal to alpha E change in T. So this is now the formula for a typical thermal stress for materials that are free to expand. However, it changes when the material is restricted, and we have examples for that. Okay, so in the next video, in the succeeding videos, there will be examples for thermal stresses. Thank you.